generally, my problem was like a niche problem in AI. This is something that is, let's say, some kind of complement to much bigger issue of machine translation. This is more related to transliteration of a particular part of language that is quite important, but not very researched. This is proper names. So idea is that, for example, as you now pronounce my name Lauc, of course, you can't pronounce this in my native language. And this is often the problem in many other areas when human language, natural language is tried to be rendered into other culture and other language. So this is in this stage, as we managed to develop up to now. Idea is to reverse one well-researched problem. This research problem used to be major focus, at least before this end-to-end text-to-audio and audio-to-text models are developed. This is how to convert graphical representation, so the text in some language and some script, to International Phonetic Alphabet, IPA. So as you can see on this front screen, on this home screen, you have these different Maria names in different languages, and it approximately corresponds to different graphical representation, graphical rendering in world languages. As you know, there are many world languages. It depends how you count, but at least 6,000 world languages are in usage now, and at least a few hundred scripts are really researched. Okay, so I will try to do a short presentation because it's a bit of a niche of interest. So I suppose it is not very interesting to all participants. So generally, I will give short motivation. Then I will try to provide a short overview of our main contribution. This is not so much in creating new neural models and new learning techniques, but more of simple data preparation. And then I will provide present metrics of the model and our plans for the next steps. So what will be the problem? So to put it most simply, idea is how to convert name from one language to another language without butchering this name, that is often happen. So it includes pronunciation, meaning, and all other aspects, how you can represent one name in other language. In this stage, we were focused on finding the most similar rendering of the name in other language that will sound most similar. So idea is that if you transliterate or in some way, let's say, render name in one language, let's say English, to other language like Japanese, Chinese, to find the most similar string, the most similar string of characters that will, when read by native speakers in this target language, will sound as similar as possible to the pronunciation in the source language. So this is like roughly set the problem. It has many methodological issues because this concept of similarity is quite fuzzy. So there is no one well-accepted methodology how to measure similarity, and especially phonetic similarity. This is the reason why many linguists, for example, don't consider this as some serious problem, because similarity is quite subjective. But we believe, although we accept it's subjective and it's contextual and so on, that still this is an important problem, and this is not only technical problem how to transliterate or translate name properly, but also culturally important problem how to appreciate another culture and not change some person name to completely unrecognized form. Regarding the particular application we were focused on. This was actually the motivation for whole project, was measuring the quality of transliteration. So it was tied with one language. So I was involved in the project that was developing transliteration of Thai words to Latin. It's called often also Latinization or Romanization. So how to render Thai words, particularly names, but also other words as well, to the Latin, or they sometimes say English, but in general it's Latin script. So this is one big area of application. So how to help in transliteration of different languages to not only Latin, but all other scripts as well. For the big languages like, Chinese, Japanese, Korean, there is these official transliteration systems. Sometimes they are good, sometimes they are not so good in this, let's say, objective of rendering pronunciation in the target language, that is usually English, correctly. Another area where this is also applicable is different onomastic research. So this is something that is often uses some kind of etymology of the names, of origin of names, where this phonetic similarity is quite important. And lastly, related to this conference, this is also important area in information and text retrieval, where you need to retrieve the names that are written in different variants. So typical example is Chinese, where you have multiple renderings of, most of them are not very good, but they all try to sound in English as close as possible to the original Chinese pronunciation. So matching these different variants in the text is extremely important when information retrieval task is focused on retrieving proper names in the wider context. So both human names, company names, location names, brand names, and so on. So what we developed is exactly model that is reverse of well-known problem that is called G2P. G2P means grapheme to phoneme. That is, you have like text in one language, and you need international phonetic representation of this text, how it will sound. And there are many systems. We use some of these systems both in evaluation and data preparation, but we didn't find, and this is why we developed the reverse model that for the given pronunciation will provide text rendering of this pronunciation in the target language. And depending on metrics, we believe that we developed it properly. I can even try to make short demonstration if this is possible. So, for example, this is. Can you see the new screen, or presentation is still visible? Okay, I hope that new screen is visible. So this is like short demonstration of this model. You have English name Richard in IPA notation, and if you want to see how this name will be written in other languages, then you can see this different rendering of name Richard in few selected languages, but you can add others as well. For example, let's add Thai. So this will be Richard in Thai. Let's say, I don't know, Korean, and so on. So this is actually what model is doing. What we have done to achieve this, actually the biggest issue was how to prepare a training data set for the more or less standard sequence-to-sequence model. simple solution at the beginning was just to use existing G2P datasets. There are a lot of these G2P datasets, but this is not enough because there is a huge variance in how these phonetic scripts are written. So we developed two helper models. One model is embedding of IPA notation into this, let's say, sounding vector that will be similar and find other similar API pronunciation source strings. This was one model, and second model is model that actually cover some kind of more like notational variants in API, because different data set use different variants, and they were not covering like all richness of this phonetic representation. And our final result is, let's say, satisfactory and at this stage. So standard metrics that is perfect for, like, say, Latin languages, not so good for languages like Chinese, is character error rate. So this is actually how many characters the model has missed from in the test data set. Similar metrics that is more used in machine translation, BLEU metrics is also, let's say, pretty okay for these initial models. And this is especially if we take into account not only the first result of the model, but like top K, in this example, top 3, then there is almost no error in the rendering. So one of these top 3 candidates are something that we have in our test data set. So just a few words on data sources. So we just collected all publicly available free data sources, and then we did some kind of quick cleaning, standardization, and, let's say, improvement of this data set. And finally, the final data set was about 5 million different language string API triples. And then using this data, we developed these two helpers models that at the end double the number of examples, number of data points that we fed our model on. The one is this already mentioned embedding of different APIs into, let's say, multidimensional vector with the objective that similar vectors measuring by dot similarity represent similar words or similar pronounced text in API. So this was one model, and we got about million new example, but we multiply this in two stages with combining other models. Second model is simple sequence-to-sequence model that was just used to cover all these different variation in this phonetic script. So most of variation was related to vowels. So, for example, for sound A or E, there are about 4 or 5 different API similar sounding sounds, how close it is, and so on. So this is something that this model covered pretty correctly. Okay. The final step that we done was a result of testing first model. So when we test first model and provide our team, actually this was done on Chinese and or Thai language first, and when we provide our members of team with the possible outputs of this our sequence-to-sequence model, we provide up to 10 first examples. It was not always that the first one was the best according to them. So we just generate at the end 50 of different models and use two sources of, let's say, reinforcement. One source was phonetic distance. So there are some algorithms that are not perfect, but that measure how two API strings are distant or similar to each other. And the other was just human input that some native speaker of the target language preferred not the first result, but the fifth result or sixth results. So we just collected all these examples and then add this, remove these initial examples from the initial data set and replace this with these new targets. So this is like these three aspects of the model. And regarding the implementation, this is more or less standard. So we used byte-based. So with our vocabulary is bytes. So this is not so recent model made by Google initially, based on this, let's say, the most widely used sequence model T5, but vocabulary is not some like 2000 or similar vocabulary. Vocabulary is just byte-based. It covers all the languages much better. So as you see, this is quite a short sequence, so it was not very demanding for model transformers. And we use standard, more or less standard parameters, both for training and for inference. So when you check the what is interesting error rate by language, you can see interesting patterns of something that linguists call orthographic depth. Orthographic depth is actually how far is representation, graphical representation of some language from actual phonetic pronunciation of this language. So you have languages like Spanish or Italian or more or less all Slavic languages that are very close to actual phonetic pronunciation. So there is more or less rule-based, simple way how you can pronounce a word in that languages. In some languages like that has like complicated history of phonetic development, like French or English or Chinese or Japanese, have much more of this phonetic depth, of this distance from graphical to phonetic representation. And actually, there was interesting correlation between error rate to this depth of language. So when you zoom in onto a few particular cases, so as you see, a language like that are shallow in this sense, have almost zero or exactly zero error rate. So they are more or less rule-based. So there is one proper way how you can write some sounds, some phonetic representation into this language. And other languages are much more challenging, especially Chinese. Although for Chinese, and this is something that we are currently working on, it is more subjective of how to render this phonetic representation, because there are many correct one, let's say. So this is about present state. So what we learned from this research up to now is that this idea that was beginning of motivation of whole project, how similar two sounds are each to other, are actually very subjective and contextual. So, for example, to some Japanese speaker, right and light sounds almost similar. because they don't distinguish these two sounds. For other speakers, this is completely different sound. For some speakers like English, the length of vowel is not so important. For other, like Thai in our case, or Vietnamese, it completely changed the meaning of the words. So what we are now working on is some kind of methodology of measuring phonetic similarity, not as a binary relation, but adding additional argument that is native language. So actually it will be how similar this API string is to the target API string for the speaker of Japanese or English or German and so on. So we are working on that, and we are extending our data set so to improve more training data, and especially for these underrepresented languages. Okay, so this is more or less about that.